So next up, we have three people: Hyomin Kim from NJIT, David Witten from Tapper, and Frankie Bonte. She's a high school student from DeSales High School in Ohio. So I think Hyomin's going to start off the presentation. Is that right?
Hi, good morning. This is Hyomin Kim, assistant professor of NJIT. We're going to talk about development of magnetometer, which mainly led by David Witten, who is online. So I'll be talking briefly about what the goal of our magnetometer project is, and then Dave will run the rest of the session, and Frankie will show some of her work that she did. So if you, Dave, can you share your presentation slide, because you will be the driver for the most of the presentation. So
what we've been working on is magnetometer support for the personal space weather station and other related projects. We have myself, Frankie Bonte at DeSales, and Dr. Kim is acting as the overall advisor. We have specific goals to establish a densely spaced magnetic field sensor network to observe Earth's magnetic field variations in 3 vector components. The target performance level is set at around 10 nanotesla field resolution at 1 second sample rate. And by way of example, the Earth's magnetic field ranges from 25,000 to 65,000 nanotesla. So you can see that we're going for quite a level of sensitivity. The time varying field measurement is sufficient. Absolute measurement is not necessary. As far as the physical magnetometer support port and extender that I've been working on, the specific purpose is to support the personal space weather station. There is a smaller version of this that doesn't have the extender component, that's less expensive and simpler to work with. And it's also prototypes exist of that as well. And it's easy to attach to a Raspberry Pi or Arduino or something for other kinds of projects, perhaps school projects. The sensors used in either case is the PNI RM3100 module. We're using it as the module at this point. At some point, we may switch to having it manufactured with those module components directly on the PC board. It includes a microchip MCP9808 temperature sensor for calibration and characterization purposes. The interfaces that we're using for this purpose, we're not using the SPI interface. We're using the I2C communications available from these components and polling them at about 1 second intervals. The remote extension is quite clever. This is credit goes to Tom McDermott and 0AX for this. We are able to use I2C over a shielded Cat6 cable to extend this away from any other interfering documents, seemingly at up to 100 feet, 30 meters, whatever, or more. We have not totally tested this, but it appears to work well. And for the full personal space weather station, 2 boards are used with 1 magnetometer module and a shielded cable to make the extension. So we've designed this in such a way that one board connects directly to the data engine or whatever other device you wish to hook it to via I2C, and two boards, and the other board actually has the magnetometer module and set in a remote mode and placed physically away from the other equipment. These are early 3D mock-ups of the boards. They don't show some of the headers that support the magnetometer, but they give you a general sense of what the current state is on this bit. There's several connectors on here. There's a PMOD connector for directly attaching to the data engine. There's there are two of they're JST SH connectors that are, they're not populated in this view, but they are similar to the SparkFun Quick or the Adafruit, oh, they've got some name for it, Stemma QT, I think. And there's a Grove type connector on here too. So it's easily attached to other types of projects besides the full-blown personal space weather station. We're doing this in hope that people will find other uses for this beyond the direct, you know, our obvious intention. The magnetometer module itself, as we're using it, is a 3-axis magneto-inductive measurement module. It's very low cost. Even fully built up modules are about 20 or less than $20. And so that should allow us widespread deployment. They're physically very small. They're essentially 1 inch square by 8 millimeters high, and much smaller than most other sensor types that we have access to. They're high sensitivity. The manufacturer claims 13 nanotesla with the default settings. We hope to tune that perhaps even better. I'm sure that is dependent on the setting, but it gets us into this right ballpark, and nothing else does at this cost. The board itself supports native I2C or SPI interfaces, but in this case, we're only using I2C. This is actually a setup that I've been using for electrical testing, or making sure that the basic functionality is working, not for evaluation of function. But and this shows an Odroid N2 with a SparkFun P-hat to expose the quick interfaces. This has also been tried with a Raspberry Pi and an NVIDIA Xavier, and probably a Nano as well. I haven't really worked on the Nano much, but so it works with a variety of boards, single board computers. The extender function, this is probably the most interesting bit, at least creative bit. The I2C bus was created to provide a very short range, less than a ½ meter serial communication between boards in a chassis, and was not designed for high speeds or long lengths or high degree of noise immunity. The PSWS and similar projects need to be able to separate these things. NXP makes a PCA 9615 chip that converts I2C, the standard single-ended I2C signals, into differential signaling, and allows the use of an independent voltage for the link. So it makes a differential link, and we're using the differential link at 5 volts across two wires in the cable to give enough headroom to power the remote board without having to have a power supply out in the weather. And then NXP calls this an I2C to D I2C converter, and we convert to differential for the extension, convert back to standard I2C at the remote. There is potential within the limits of the headroom, which haven't been determined, to attach other very low power draw components at either the local or the remote end of this bus, but always within the limits of the available power. This shows specifically the I2C extender chip. This thing's a pain to solder. It's about the limit of what you can do by hand, and I throw away a couple chips for every one I get right. But so ultimately this will go to automated manufacturing, and hopefully this will be better. The temperature sensor is a simple but fairly high accuracy sensor that will give us information about the operating environment. The one on the local end will tell us the operating environment of the data engine and other components. The one at the remote end will tell us about the operating environment of the magnetometer itself. It appears on the same I2C bus and requires no additional circuitry, so this was very simple to implement. And here's the location.
5 minutes.
Okay. There's more needs to be done with software driver development and more evaluation under realistic conditions. Had some references to the pages. And that's the extent of my presentation. See, how do I unshare? Then I wanted to give some time, if she's available, to Frankie Bonte. She and also her father have been working on some characterization of this, and I'd like, if they're available, perhaps they can give us some information on what they've been up to.
Yes, thank you so much, Dave. As he introduced me, I'm Frankie Bonte, KE8 HPA. Can everybody hear me? Can you hear me all right?
Yep, you sound great.
All right, perfect, thank you. Okay, so I kind of wanted to talk a little bit about the data that we've been able to collect. So first of all, we wanted to start out making sure that we were able to get data before, even correctly orienting the setup. So I'd like to show the setup that we have. If you can see this. So over here, we have our, the kind of setup that we have in the beginning. So as you can see, there's the real-time clock, and then the SD card. And over here we have the magnetometer support board that was provided by Dave. So thank you so much for that. And so first of all, so in order to get data to the computer, we would have to take the SD card out to put it into the computer or use a serial connection. But so I'd like to show you some of the data that we've been able to collect. So on the computer here, here's each line of data, and each line of data has the real time and date. Oh, the computer turned off. I apologize for that. Okay, so here we have the real time and date, and then we have temperature in degrees Celsius that we got from the temperature sensor, and then XYZ readings in in microteslas. And this is all in the CSV format, so it can easily be put into a spreadsheet later on. So that's just the data that we were able to collect before actually putting it out into like a test field. But we were able to make this box that we hope that the magnetometer would go in the future. So it has, so it's waterproof, the connection, there's a cable for it to go out, and we placed it on a concrete block so that whenever we set it outside, we will be able to face it north and level and plummet to get the best data from the magnetometer, and it'll be in a fixed position outside. However, because the data that we're getting, it has to have a serial connection directly to the magnetometer, our kind of next steps in the future will be to get the magnetometer placed in the box in a set position, and then also to be able to have the system communicate directly to the internet so that we can share our data with other people without having to have the serial connection or use the SD card to take it out and put that information in the computer. And also that will be super helpful to show that this is the data from our position, and then we'll be able to share it with other people around the world over the internet. So that's kind of the setup that we have over here, and hopefully in the future we will be able to get that connection and get the magnetometer set up outside. I'd just like to thank Dr. Kim and Dave for including my dad and I on this project. So thank you so much.
That's great. Yeah, thank you very much for the demo, and really great to see all your setups, including your HamSCI mug, which we're talking about right now. How exciting to see the HamSCI mug. So yeah, my concluding remark, since we are running out of time, but my concluding remark from my side is that so magnetometer can vary in terms of price from say a couple of dollars to, easily like, hundreds of $1,000s. So instead of having a really fancy, high quality magnetometer at some point in one point, our proposal is to distribute very inexpensive, very easy to use magnetometer all the places to see how the magnetosphere ionosphere coupling system responds to the space weather system. So that's the goal. So that's why we want to go route to this type of like really inexpensive magnetometer. So it's great that high school students and other amateur ham radio scientists are involved to establish like really largely spaced, densely spaced magnetometer network. So that's the goal. So back to Nathaniel.
All right, thank you so much, Hyomin. Thank you to Hyomin. Thank you very much, Frankie, and thank you, David Witten. It's a great presentation, and I did get to see the magnetometer in person when I went to Orlando Hamcation this year. And so it's nice to see actual hardware coming out of the project, and it's nice to see it get into the hands of people like Frankie and her father to actually see them testing it and trying it out. So it's very good.